I'm not getting paid right now.
I don't wanna fall in love. I just wanna have some fun, yeah. I don't wanna fall in love. I just wanna have some fun. I don't wanna fall in love, 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 fall in love. I don't wanna fall in love. I don't wanna fall in love. fall in love. I just wanna have some fun, yeah. I don't wanna fall in love. I just wanna have some fun. I don't wanna fall in love.
Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. We are doing some more GRE work tonight, trying to talk a bit about trigonometry and then answer the questions in Cracking the GRE Math Test from Princeton Review 2002. Yes, it is 24 years old. What's your point? Okay, well, 23 anyway. All right. So, to just basically cover what we were talking about before, these other bits on this page, we were cool. We were saying that when we started talking about trigonometry, we also talked about geometry quite a bit in order to better understand the history of what else was going on. We were talking about Euclid and his contributions to mathematics from the roughly 300 BCE era, and how if we were to eliminate the fifth postulate, which was the thing that was giving us a little bit of trouble in order to figure out, like, okay, how could we just create this seemingly ex nihilo out of nothing and expect nobody to, like, raise an objection to it? Lots of people have raised objections to it in the past several hundred years, well, a couple thousand years, in fact. Main idea, why is it that we're not able to just get on without the fifth postulate? Why do we need it? So all of the other first four postulates of the five that are total seemingly are like self-evident bits of information. Again, we can draw 2 points and draw a line between them. Right, that's number one. Number two was that we were able to harumph. Okay. Break out Euclid again. So, postulate one is to be able to draw a straight line from any point to any point. So between 2 points, you can always draw a straight line. Second is that any line that you have on a piece of paper, remembering line to them really just meant like what we would call now a line segment, is able to be produced indefinitely. So it could just go forever in whichever direction you want. It can be chosen to be one direction, in which case it's a ray, and it can be chosen to go in both directions, which gives us our modern line. 3, describe any circle with a center and a distance. So, a circle will be uniquely defined by a location, its center, and a distance, its radius. 4, all right angles are equal to one another. So no matter where you draw them, no matter, anything at all, no matter where they are, those right angles will always be the same thing. And postulate 5, that if falling on a straight line, if a straight line falling on two straight lines makes interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, will meet on that side where the angles are less than, or on which the sum of the angles is less than two right angles. So, it's a mouthful, it's ridiculous, but it's also 100% necessary. Because when we say, all right, look, if we sum up these two angles, they're going to meet on that side, and only that side, then this is some place that has no curvature. This is going to be our planar geometry. If we have anything else, if we have a positive curvature, i.e. spherical geometry, or if we have a negative curvature, i.e. hyperbolic geometry, it turns out that we get two completely different structures than our planar geometry. Since Euclid was only really equipped to work with planar geometry, that's what he formalized. And it took another 1,000 years, basically, 1,300, in order to finally work out a formalization and a treatise to get spherical geometry well in hand. That was Al-Jayani, who ended up coming up with the treatise, or the first major treatise on spherical geometry. And Lobachevsky and Bolyai, Janusz Bolyai and Nikolai Lobachevsky were the first two people to really come up with a formalization treatise on hyperbolic geometry. So we have that negative curvature, where if we have one line falling upon two straight lines, in hyperbolic geometry, these two things will diverge from each other on both sides. And so we end up getting something that is open on both sides like that. In spherical geometry, we end up getting closed figures on both sides. So eventually, we end up making triangles on either side of that transversal. And yes, the sides of those triangles are curved, but that's not really the point, right? It is a triangle as defined on spherical geometry. There are three straight lines connected at 3 points. It makes a triangle. Okay, so hang on, let me copy this thing, because I rather like having at least some of the basics. Alright, now we reset the canvas. Get our stroke width back to 0 there, get that one, and then we paste. Excellent. Alright, we can take this out. Don't need them. Okay. So, the way that our trigonometry is going to work, and this comes mostly from my experiences over 15 years of teaching at community college. You know, if it works for you, great. If it doesn't, then maybe figure out why this makes sense if it doesn't. See if you can at least understand it, even if you don't necessarily like it. Okay, so we have a point on a circle. We call this, in fact, it doesn't even matter what circle it is. We can let this just be r, so it is a distance of r away. That's our radius. We have our x and y distances, which represent the Cartesian coordinate distances, where our point can have an altitude drop down to the x-axis, and the x-axis will intersect with the altitude at some point. So that's going to be our point there. We know that this distance coming across here is going to have a value of x. This distance here going up and down is going to have a distance of y. And now we have a right triangle that is not inscribed, but it is connected directly with our circle at some point xy. It does not matter which quadrant it's in. We do, however, formalize this to say that this is going to be our positive angular direction, going in a counterclockwise direction, or anti-clockwise, those of you who are from the UK and many other places. All right. So as we go around the circle, we're going to run into, well, really any number of locations where we get the exact same setup. Where we are going to go from the origin out to some point x comma y. This is going to drop an altitude. We end up with a right angle. It has a radius r. It has a horizontal distance x and a vertical distance y. Now granted, these are going to be different from each other. That's why they're in a different color. Right, and no matter where we actually do this, no matter what quadrant it's in, again, we get the same setup. Yeah, it's too close to the other one. Don't want to do it like the other one. Alright, this is going to be x here, this is going to be y here, this is at the location x comma y. Right, we can end up having any one of these situations. We end up with these angular values. No matter in which quadrant we have our theta, it's just going to be represented by whichever version of this we have. These are all different theta values. They give us all different x and y values, but the r value naturally is going to be the same no matter where we are. It's a circle after all, so if you have a point on the circle, then every point on the circle measured to the center is going to be r, right? It's going to have that distance r. Okay, so then, what we would like is to then come up with a way in which to measure a particular angle theta and the particular distances x and y that we have for any of these points that we get on the circle. Again, r will always be the same. So, one of the things that we can do is we can scale everything down. Or up, depending on which way we need to go. What we're doing here again, either scale up or scale down. Hang on one sec. Let me take that. Turn all of that. And then we make it thicker. It's terrible, but you know what, it will work. Okay, so with our now orange lines, what's happening here is that we now have a whole bunch of proportional values. So this angle here is still theta. It's the exact same stuff. If we need some sort of proof that this is in fact the same, right, we have scaled this up or down depending on whether r is larger or smaller than the certain value we want. And it has a right angle at the bottom. And all we did was we took theta, wherever it is, and then made that section smaller. So it's just now looking at a smaller section of it. It overlaps with the previous theta. So now our right angle is the same, and our theta is the same, which also means that the complementary angle at the top corner is going to be the same. So what does that mean? That means that this triangle is just a scaled down version of the other one. Like I said, that's what we're going for. It's our goal. But what that means mathematically is that these two triangles are now similar. So all of their side lengths are going to be proportional to one another. Right? We can scale this all down until we get a radius length of 1. And when we get a radius of 1, this is going to get us what we call the unit circle. All right, what about this point here? Well, it's no longer at x comma y because x and y are over there. But what is it? Well, r got scaled down to 1. So therefore, x is going to be scaled down by a factor of r. So this is now going to be x over r. And y also got scaled down by the same factor, y over r. Y over r is the point. Or the distance, I suppose we can call it the distance. Right, so x over r horizontally, y over r vertically, and r is equal to 1 now. How does that help? Well, most of the time we do stuff on the unit circle. So we start looking at, what are all the patterns going to be on the unit circle? So when we look just on the unit circle itself, right, this is x over r, y over r, where r is equal to 1. These are all new x and y values. I guess really it should be, the original r, not, so you're not confusing it with this r here, like r0, which can do that. This is literally R1. no, didn't want to do that. Right. Or let it be R sub unit. And, okay, the unit circle is going to have a radius of 1. So this is now Oi. Alright, x0, y0 divided by each r0 is going to get us then a point that we could just call x comma y or x sub u if you wanted. I really wish it would not assume that I'm trying to close those. Stop it. X sub u, y sub u. Whatever you want to call it. However you want to make it work. You could just call it x and y and leave it at that. It's all good. But the real point is, right, we just get some x and y coordinates that are on a unit circle, has a r value of 1, and now we can figure out some relationships that exist on this thing. First and foremost, one of the things that we can do is start talking about our angle theta in terms of real units. And by real units, I mean we don't want to use units that seem somewhat arbitrary. So, for example, they're very nice, but degrees are essentially an arbitrary unit. The degree measurements of 360 degrees come from Babylon. So this is ancient mathematics. Why Babylon? Why 360? Well, if you think about it, 360 has some very nice factors. And these are the kinds of factors that we would like to split our circles into. So stuff that's easy like 2, 3, 4, 6, 8, 16, you know. Any powers of 2 are real simple. The other ones, maybe not. Right, qualifier. They are evenly divisible. 360 is evenly divisible by 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18? Yeah, 18. Probably 16. No, not 16. Right, if we divide by 8, then we end up getting 5 on the end. So it's not divisible by another 2 after that. Right, it's 45. Oi. 18 and 20. And there's more stuff beyond that, but it's fine. Namely, like all of the other numbers that we're multiplying by this stuff to get 360. 18 and 20, right, are the middle factors. So, after that, it's 15 times what, right? For 360 divided by 15 is going to be the next number after 20. And so on and so forth until we get all those values. But here, nonetheless, right, that is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of the first 20 numbers. And in fact, 13 because 1 is technically going to divide evenly into 360, even though it's ridiculous. Of the first 10 numbers, the only number it skips is 7. Right, so 9 out of 10. Really good. And then we get 13 out of 20. Also really good. Compared to a lot of other numbers that are out there, you can't really say that. It's also kind of like a nice number because it ends in a 0. It's also not humongous. So, like, you could tell what a degree is, give or take. Whereas ancient Babylonia actually was working off of a sexagesimal system. G. I mean, I can count to G, but... Alright, this is a base 60 number system. So what does that mean? It means that it had 60 different numerals that you could write out. 60 different arrangements. I don't think we have our triangular crayons still. We do have our Play-Doh. Oh, we do. I think I've done this before on stream, but it's been a while. Probably since the last time I did it in person. Let's see, we need like a darker color maybe. Hey, and something that's not completely dried out. There's a smell of the 80s right there. All right. So, in ancient Babylonia, you'd have a clay surface like this that you would take, and then you would take a stylus, which has, for instance, a triangular shape to it. Hashtag not sponsored. And basically you'd take this, have your thumb along the flat side, and then you'd dip it in until you get a nice little triangular divot. So here I have 3. I don't know if you can actually see that, but the stream's also behind. Come on. Yeah. So we see 3 right there. If we wanted to continue, then we'd put 3 more directly above it, and 3 more directly above that to get 9. Alright, now here's where my Babylonian math breaks down. In order to get higher numbers, we need... Next question, where is my copy? Huh. I have all the Irving Finkel books. You think that I was studying ancient Assyria. Let's go like this. So what do we want? There we go. That's the picture I want. Right. So when we do something like this, we're going to have to know ahead of time what number we're actually doing. Mostly because this is not quite how things work. Right, so everything's done in batches of 3s, first of all. Then, when you want to do a different number, then we need to write out in, in batches of 10, we make 1 mark diagonal, and then 1 mark diagonal up and away from it as well. So it makes kind of a arrow, sideways arrow shape like that. That. So it's going up and away from it, both up and down. Made with this triangular stylus. It's gonna look something roughly like that. So then each of the 10s that you make end up having one of those. So it is sort of like partially decimal in that there's a repetition in the shapes. But what would happen is if we were to, and it's very easy to, I mean, it's kind of time consuming, but it's very easy to erase as well. You just kind of mush the clay over the top. My son's got some modeling clay. Could probably do that too. He just got, like, you know, the real stuff. So anyway, for every 10 you do 2 of those little strokes that bend away from each other, make a sideways one. And so if I want to do like 35, I do something like that, where we get 3 of these sideways ones, 1, 2, 3, and then we've got 5, which are set as 3, and then 2 more underneath them in between. Right, so we can get up to 59 doing this. After that, it becomes just so messy that they were like, all right, that's it, we're going to start over. And they put the 60 as a 1 over a bit. And then the question then starts becoming, how many 60s do we have? Then how many 1s do we have? So they started a place value system. Now, unfortunately, that does also mean that they had I mean, they had to do a little math in their head to figure this out, but many of them just kind of already knew what the multiples of all these numbers are, so it wasn't an issue, really. However, if we wanted to figure out what this was in, let's say, the current year, in sexagesimal, then what we see is we are in 2025. We want to know how many 60s there are in this year. So that's going to get us a, what is that, 3? It's going to be 180. So that's going to get us a 22. That's 225. How many 60s are there in 225? I think that's also a 3. Yeah. Is a 180. Subtract that. That is now going to be a 45. So the way we track this is we need to write a 33, and then we need to write a 45. So 1, 2, 3. 1, 2, 3. And then a 1, 2, 3, 4. 1, 2, 3, 4, 5. Alright, so let's see how this turned out. So we've got over on this side 3 for 3 tens is a 30, followed by 3 gets us 33. So 33 60s, which, right, I probably should have done that out. Hey, Mint Toby, how's it going? Welcome on in. 33 60s is going to be 18 and 1 is 9. Yep, that's a 1980. I was just having a conversation with a lady who was turning 45 this year because her birthday was 1980. Should have probably remembered that. It's fine. Right, so our... Oh, come on. No! There we go. Apologies. I'm just going to yell at my equipment. It's fine. So we have our... What just happened? Oh, that's what... Yeah, okay. Apologies. I'm fine. Yep. So what we see in the Babylonian world is that we've got 3 10s and 3 1s. Gets us 33 60s, which represents the number 1980. And then we've got 4 10s, 1, 2, 3, 4 going down, and then 5 1s over here. So 1980 and 45 gets us to 2025. So the Babylonian cuneiform number system, I mean, it's not without its flaws, right? We write 4 digits to represent the number. They write 3, 6, 10, 15 symbols. So, like... Yeah, point goes to us here, I think. This is going to be how that works. And again, this is a base 60 number system, so they have 60 different ways of arranging symbols to make individual numbers. Yes, it made sense at the time. Perfect. And so much of human history is it made perfect sense at the time. Oh my goodness. Like, how much coding just made sense at the time, too, right? For anybody who doesn't know, Mint Toby is an Elite Dangerous streamer, and go check him out sometime. We had a fun time laughing about somebody who came in and was trying to troll yesterday. Whew. Toby, not someone you want to play games with. Anyway. So why not, if we were talking about, like, you know, what candidate number do we want to use, the other option was 60 by 60, which is the third place value, right? So we would write it as 100, because that would be 160 squared plus 160 to the 0, 60 to the firsts, and 0, 60 to the zeros. So we would write it as 100. The Babylonians wrote it as a single stroke with 2 blank spaces following it. A little bit harder to do in those days because they didn't actually have the number 0. So they would just end up writing a single stroke in their clay, and then like leaving a couple of blank spaces, and then start writing after that. Again, it made perfect sense at the time, and if you're thinking about it, it's context dependent. So rather than us, in our civilization, we're very explicit about what numbers we're using all the time. You know, the year 2025. Most people, if you just wrote the year apostrophe 25, back in 25, if it's today, people would be thinking, oh, you mean like 1925? 1825? It's context dependent upon what other types of stuff you're talking about. And the same thing was going on back in those days. You didn't have, it's 60 squared is 3600, not 360. So even that, right, is everything's off here just by a bit. But the idea was that everything was context dependent. If you wanted to talk about 3,600 troops that you wanted to move from one place to another, you just write a single stroke and leave a couple of blank spaces, or leave sufficient blank space for the person to realize, oh, you mean a big number. Not a small number, quite a big number. And back in those days, you probably weren't going to go another 60 times this, because 60 times 3,600, I believe, is 216,000. Yeah. Yeah. No. Damn it. 60 cubed. Yeah, okay, I was right. Always doubt yourself. For little things. Right, so it wasn't going to be 216,000, because that's like, more people than you probably have in your city. But 3,600 would make sense as a number of troops. 60 might be like, oh, we're expecting a massive invasion. Send 60 guys. No, clearly not. That's not what they mean. We're going to send, 3,600. All right, that makes more sense. Right. So when we're talking about like doing angles, in Babylonian, you had this 360, which, like, I think I understand the degree mark. Unless, of course, that was just a coincidence, or it was invented later. Is it just 3,600, but we're talking about tens of degrees? That would be wild. All right, I think I need to go consult people. Go find some historians. Anyway. But anyway, they used 360 because 3,600 also meant that like 1 degree was the like size of a human hair, basically, going around this individual circle. That's too small. We can't easily make that picture. We can't see that in our minds. We can't put it on paper. It's too hard. So doing it as 360, 1 degree was like, a certain amount of time that goes by, how far the sun moves in that amount of time. We could figure that out pretty easily, right? It goes 360 in 24 hours. That is evenly divisible. It's going to go 15, nice. It's going to go 15 degrees an hour, which means that it's going to go a quarter of a degree, right, every minute, or 1 degree every 4 minutes. So if you were to watch the sun track across the sky, right, 1 degree every 4 minutes. That's a pretty reasonable amount of time to try and, like, you know, scope out how far that's going to go. All right, so then when we start talking about, like, again, degrees are going to be essentially arbitrary in terms of where they all come from. So we don't really want to use degrees for a mathematical context. They work fine. It works great for latitude, longitude, all that good stuff. But, again, kind of arbitrary. So instead of just marking out a certain amount of distance that we like and calling that degrees, we're going to go and use the arc length of our circle in order to find where we are on the circle itself. So we go over here, we say, like, this distance that we travel along the edge of the circle on the unit circle is going to be identical to the angle that we have opened up at the center. So our theta over here is going to be the same as our distance, the arc length on the unit circle, theta. So then we say, okay, what values can we put on this? Well, if we go all the way around a circle, right, we've measured this out for millennia at this point. We know that going around the circle once is the circumference. Bingo, Rex. Right, 2 times pi times r, which ends up in this particular case just being 2 pi because r is equal to 1. So here, if we say, all right, we're going all the way around the circle, then going all the way around the circle is going to get us a angle measurement of 2 pi. So theta equals 2 pi. Now, if we do that before we even start, naturally, right, theta is equal to 0. 0 here, 2 pi here. So let's make it super easy. All right, let's cut it in half. So that means on the other side of the circle, when we've only gone halfway, theta is going to be equal to pi. Because, again, whole thing is 2 pi, only half of it is just going to be pi. And then we go half that distance again. Right, theta is equal to pi over 2, because it's half of pi, right? Easy enough. Then, look at the pieces we just made. Right, these are quarter circles. So, now we've got, sure, let's go like that. We've got pi over 2 to do the first bit, 2 pi over 2 to do the next bit. That's equivalent to pi. We just wrote that. And then we make a third one, 3 pi's on 2. Right, 3 pi's on 2. And then we go another one, we get back to the beginning, and now we're at 4 pi's on 2, which is 2 pi. So we can verify it using the pieces that we create as like a single unit, and then we just stack them on top of each other until we get all the way around the circle. Okay, so then easy one again. we're going to go half that distance again. Give or take. Okay, so this is again half the distance of 0 to pi over 2. We're only going half of pi over 2 or pi over 4. Right, so now make those the slices that we take. We got pi over 4, 2 pi over 4. Go straight up. 2 pi over 4 is pi over 2. Cool, we just verified it. Go tick over again is going to get us 3 pi over 4. Puts us there. 4 pi over 4 is going to put us horizontal again, and 4 pi over 4 is going to be just pi again. 5 pi over 4 puts us straight back down here again. Thanks, Rex. It took a long time to get here. This is the other thing, right? It's that, like, I don't have a time limit. Okay. Close enough. Okay, so we took another piece and went down. That's now 5 pi's on 4. And then we go another piece. That's going to be 6 pi's on 4. What's 6 over 4? It's 3 over 2. So we're just straight down again, back to 3 pi over 2. Take another one. That's 7 pi's on 4. Blah. That one's gross. Okay. Theta here is 7 pi's on 4. And then tick over again, 8 pi's on 4. 8 over 4 is just 2, so we're back to 2 pi. Okay. Now, the other ones that we're going to do are not going to be, oh, cut it in half again. Yes, we could do that. However, at this point, the remainder of these things become awkward. So instead of cutting it with pi on 8, what we're going to do is cut the remainder into thirds. So we're going to have one about here. I hate cutting thirds. It's the worst. And then half of that. Here is 1, 2, 3. Damn, that is so close. All right, we're going to call it. That's good. Okay, so we get one here. We get one here. And then we do the same on all the rest of these spokes. It's going to... Oh, wait, I just used my fingers. Here, here. Pretty good. Here. Okay. Here. Damn, that's so close. I'm getting better in my old age. That one goes there. That one. 3 minutes to lads. Okay, So where does that get us? Well, if we cut out all of this nonsense, because we don't need it right now. Okay. That's going to put us here. Theta equals. This is going to be pi over 6. So what that's going to do is it's going to get us right, it's going to be a third of the way from 0 to pi over 2. Right, so we cut those in thirds. I should really color code these better, but it's alright. I only have a very limited number of colors. Let's do... Can I just do... I cannot. Cool. It's going to take too much time. I'll do it during break. It's fine. Nope. So the green ones, anyway, are going to be our pi's on 6. And again, if we mark them in terms of, here's 1 pi over 6, right? Here's going to be 2 pi's on 6. So 2 on 6 is going to be pi on 3. Right? Add another pi on 6. That's going to get us to 3 pi's on 6. 3 over 6 is a half. We're straight up and down again. 4 pi's on 6 is going to get us here. But 4 over 6 simplifies to 2 on 3. So 2 pi's over 3 is there. Add another pi on 6. That's going to get us here. That's going to be not 4 anymore, but 5 pi's on 6. 6 pi on 6 is going to get us back to pi. 7 pi on 6 is going to be here. 8 pi on 6 is going to be here. And again, 8 over 6 is going to be 4 over 3. So 4 pi over 3. 8, 9 is straight down again. 9 over 6 is 3 over 2. 10 pi's on 6 is here, and that's going to be again 5 pi on 3. 11 pi on 6 is going to be here. And 12 pi on 6 is back to 2 pi. Okay, I'm going to mark the other ones with white. We're going to take a break here. 3 minutes. Be right back. Thank you so much for coming. Thank you so much for sticking around. We'll see you in a bit.
Rating party!
Hello, everybody. Anybody who can hear me, thank you so much for coming on in with Zach. I'm going to redo this once the ads are not playing. Ads should be playing right now, so very hearty apologies. I suppose...
I have a pen. I have an apple. Apple pen.
Thank you for Penn Center for playing your walk-on. It's an E to the 2I raid. Hey, Zach. I'll do introductions again in about 2 minutes because some people are on ad break, but woohoo! And Zach says, all right, I got one of those too. Hey, Famished. How's it going? Yeah, I know. So we get about 1 more minute. Whoa, Rex. Goodness. Let's see, are we doing... Nope, Enigma bot's still down at the moment. Oh well. So hi everybody who can actually still hear me. We got about half a minute more till everybody comes back from ads, and then we'll do all of our introductions and talk about what it is that we're doing here. Besides building a dartboard, apparently. It's kind of not building a, almost exactly not building a dartboard. Split Gate 2. Interesting. I have not played the first one, I don't think. I actually played an interesting one. It's a bit like it was called Lemnisgate. Lemnisgate. And it is a play on the term for the infinity symbol, which is lemniscate. And the idea was that you had a team of 6, I want to say. A little bit like Team Fortress in that you've got like all different classes. So you have all different classes in Lemnisgate, and you have 40 seconds to do something. So your goal is to eliminate the other team and keep yourselves alive as much as possible. So you sprint through an area, maybe there's like portals, maybe there's a bunch of other stuff, and you get the first guy set up. Then you and your opponent watch an overhead view of what the first person did. And then you select what your new class is, and now you rerun the exact same thing that you just did with your first guy, only you do your second guy. The first one is on a track, right? It's on rails. It can't change what it did, but you go back in time, and now you start your second guy, and the both of you go do stuff to react to them. And it was absolutely insane. I really liked it. I couldn't see myself spending a huge amount of time on it, so I ended up not like purchasing the game, but it is high recommendation if you ever actually get a chance to like try it out sometime, if it goes on Game Pass or whatever. So So Lemnisgate from Ratloop Studios. Like I said, I really liked it, but I couldn't see myself sinking like 60 more hours into it at least. And there wasn't really a campaign to it. There was a bunch of training, and there was a bunch of PvP that you could do, or PvE versus the computer, but the computer's just pretending that it's another human. So, David Van Housen, good evening. My name's Obi-Wan Pez. This is N-Simplex Pachinko. We're doing some trig stuff tonight, and talking about fundamental basics of trigonometry. Okay, so what about these white ones that I popped in here and then didn't really do anything about? They were originally green as well, so that was just a little confusing. It's fine. These are half the distance from theta equals pi over 6, so naturally these are going to be theta equals pi over 12 for each of those, or a multiple of pi over 12. So if theta is equal to pi over 12, then we just count up with these. So again, pi over 12 is going to be here. 2 pi over 12 is going to be here. Which again, 2 over 12 gets us 1 over 6. So same fraction. 3 pi over 12 gets us 2 pi over 4. 4 pi over 12 gets us 2 pi over 3. Again, 12 is such a nice number to use with divisors. 5 pi over 12 is not simplifiable. So here we actually do get a new angle. 6 pi on 12 is pi over 2. 7 pi over 2 is here. And then 8 pi over 12, 9 pi over 12, 10 pi over 12, 11 pi over 12. Twelve pi over 12 gets us 2 pi. 13 pi over 12. 14 pi over 12, 15 pi over 12, 16 pi over 12, 17 pi over 12. We're down here now. $18 pi over 12 is the same as 3 pi over 2. 19 pi over 12 is going to be its own thing here. Right? 20 pi over 12, 21 pi over 12, 22 pi over 12, 23 pi over 12. $24 pi over 12 is 2 pi. Right? 24 over 12 gets us all the way back to 2. All right. So like all of these fractional values might be freaking people out and things like that. I feel like throwing a dart. I know. I started saying how these were the right colors for it. I'm like, huh. The only difference is that on an actual dartboard, right, it's going to be colored this way. Rather than what I got there, but it's all good. So, anyway, the major ones that we're going to concern ourselves with are not the pi's on 12. So, everything else. The pi's on 12 end up having not so nice values that we end up finding, and we're going to have to use some of our later techniques in order to actually find those locations on the unit circle. The other locations on the unit circle, however, are not very difficult. Takes a little bit of doing, but it's not too bad. So if we take these out, yeah, you know what? We're just gonna have to copy the whole thing. It's fine. We don't need the white ones, so we can eliminate those. That'll be all right. So we're going to take out all of the white ones here. Reasons will become obvious in a couple minutes. So really, the question we want to ask primarily is, how can we figure out locations on the unit circle of these particular values? We'll leave it there. The rest is going to become needlessly complicated, so. Alright, so we already said that the unit circle is going to have a radius of 1, right? R equals 1 for every single line that we have on here, going from the center to the outside, which for finding locations is actually really nice for this point here, and this point here, and this point here, and this point here. Need to move down a little bit. Right, our 4 cardinal directions, super easy. Yeah, sorry. Thank you, Zach, for the raid. There we go. I said I was going to do introductions after the ads came back, and then I got distracted. No surprise. Thank you, Zach, for the raid. Hey, Penn, welcome in. Hi to everybody else who came over from Zach's. My name's Obi-Wan Pez. This is N-Simplex Pachinko. We do math every Monday, Wednesday, and we do games on Fridays, and whenever else we feel like it. At the moment, I'm in the middle of updating my YouTube channels. We have the @Obi-Wan-Pez for gaming, and @NSimplexPachinko6542 for our math content. I haven't updated it in like a week because I've got like a pile of the math ones that I have to actually physically watch. Ugh. And then like go through and figure out timestamps and stuff. I'm going to be doing chapters and things like that on my next pass through, so it's going to be a bit. Twitch is for distractions in some ways, yes, I mean, that's true. And then my Audacity suddenly started working on my old computer again. So now I can like go online and find clips for like bit alerts and things like that. So, woohoo! Finally, I've been waiting so long to actually do that. It's ridiculous. All because the one on Linux doesn't work. Although somebody posted in the Audacity forum to me and was like, "Hey, maybe you should check this other one out." So we'll try another solution and see if that works on Linux. And if it does, awesome. That means I am well and truly on my way to get that done. There's a Rocket League sound. Do you know what it is? Scoring a goal, yeah, okay. Oh, that's fine, I can probably figure it out. You know, just start Audacity, wait for somebody to score. That's fine. Sit my guy in a corner. I was gonna say I have Rocket League on Epic, so that means I probably have the assets somewhere tucked into my Epic folder. Yeah, you'd have to okay, that's fair. Anyway, for mathematics, I worked in a community college in Maryland for something like showcasing your terribleness. Not that I'm any better, I'm sure. I have at least played a few dozen rounds with friends who are much better than I am, so that might have helped significantly. Yeah, for mathy type stuff, I've been a math teacher in a community college in Maryland for approximately the last 15 years. The last 1 year, we've been here in the UK. So, you see my tags down there somewhere. It says UK and American. So yeah, we're living in Yorkshire. It is absolutely beautiful. It hit, I think Sensation was over in your stream saying it hit 23 today. In American terms, it's about 72, 73. And people are melting. It's really funny. Coming from Maryland, where it is both much hotter and much more humid. Yep. I think back at our old place, it was 90, maybe 92? I gotta check. This is interesting. Gotta love the content. Columbia. Yeah, that's close enough. Hourly, can we go historic? Oh, you know what? They had thunderstorms today. That's fair. It said that in the shade it was like 40 or 84. So, you know, it was 84 degrees real feel and real feel in the shade, which means that, yeah, it was like raining all day. Or completely overcast at the very least. Let's see, 84, right? That's real quick. 84, subtract 32 first, question mark? I think that's right. 52 times 5/9 is going to be about, it's pretty close to 30. Or did I do it backwards? 109 degrees Fahrenheit, yep. Yeah, I owned a black car when we were back in Maryland, and yeah, we were feeling it. It was not great. Is that right? Because if we'd done it the other way, that would have been just over 9 times 5 would have been 45 minus 30. Yeah, okay. Yes, subtract first, then multiply. So yeah, pretty close to 30. And extremely humid. And fortunately today was overcast, and that's why it stayed at 30. Meanwhile, you know, in Yorkshire it's been 20, well, 23 where Sensation was. Give or take that. Right, because 68 is 20 degrees on the 2. Anyway, oh, Zach, you missed it a minute ago. I was sitting here and I was discussing the ins and outs of you know, using degrees, but at the same time degrees are arbitrary units of measurement. So we're like, we don't really like to use those. We want to use this other version, which is based on the radius, based on the arc length that we're using to go around the unit circle, all that good stuff. And I looked at this and I went, wait. Is this just tens of 3600ths? Makes single degrees? Historically, right, I have to look that up. I'm going to have to figure out if that's a thing or if it's just like, you know, if they were using the 0 as to denote, like, I'm never going to change this digit, the 4th digit of 3600. If when we translated it into, you know, one of our base 10 languages, if somebody started just turning that last 0 in 3600 into a smaller and smaller and smaller pretend 0 for a degree sign. So I'm going to have to look that up later. Talk with some historians. Okay, so where are we? The locations of each of these places. If we look at it from... Yep, we definitely melted crayons in the kids' car seat cup holders. They were like completely covered in wax. There were also snacks that definitely had some stuff that got permanently stuck in various places. I was telling the kids, like, you know, don't eat in the car, don't eat on the couch, because that just like makes stuff disappear. All right, anyway. At theta equals 0 or 2 pi, if we've gone all the way around, we're at the location, because again, our center is still at 0, 0. We're at the location 1, 0, because we've moved 1 to the right from our origin point. And that's it, 1, 0. Going straight up, this is going to be 0, 1, right? This is not surprising. The left side is going to be negative 1, 0, and the bottom is going to be 0, negative 1. All right, now comes the more interesting stuff. How do we get all of these other places on this particular circle? Well, for one, we know that the equation of the circle itself, and therefore all of the points must lie on the circle and satisfy the following equation, is going to get us x squared plus y squared is equal to 1. How do I know that? Well, if we go back up to here, this is easier, where we have this picture, we said that our horizontal bit is x, our vertical bit is y, and our diagonal bit is r. And these are the three sides of a right triangle. Have a right angle here where we have x and y orthogonal to each other, and then r is just going to be our hypotenuse. And it doesn't matter how big or small this circle is, that relationship is always going to hold. It's x squared plus y squared equals r squared. Well, we know that from, you know, basic algebra, or, well, I guess algebra 2, when we were talking about conic sections. And we also had it here when we were talking about GRE, right? The conic sections that we were doing a couple of classes ago. So x squared plus y squared equals r squared is going to be that term there. Again, r is equal to 1, so it makes it nice and easy in this case. So we have to have a bunch of points that satisfy this equation. And why did I pick these particular ones? Right? This is because, hey Viv, how you doing? Welcome back in. What we have here is a whole bunch of right angle triangles, which again, no surprise, we saw that on the arbitrary one up above, where we just picked a point. But why this point, right? Well, this point has kind of a nice angle to it here. If we were to look at the degree angle measurement for this, we have here that this one is going to be 30 degrees, because that's the same as pi over 6. Oh, that's pretty much permanent, but I've got a bit of a cold going on right now, in addition to my allergies. Woo! I leave that door open pretty much all day just to get air through here, and it works very nicely, but they don't have screens, so there's quite a lot of pollen in here, I'm sure. So anyway, this is going to be a 30-degree angle, which gets us pi over 6, if, again, we wanted to like double check that, right? This was halfway around the circle is pi, which was 180 degrees. So 180 degrees over 6 is 30 degrees. So this is now an equivalent angle in degrees instead of I'm avoiding the word for the moment, but because I didn't actually explain it in the other one. So with a 30-degree angle, what does that tell us? Well, that says that the other side of this is also going to be 30 degrees. And if we were to connect these two, we now have R and R. And here, this distance is also going to be R, because now we have a 60-degree angle here, and a 60-degree angle here, and a 60-degree angle here. This is now an equilateral triangle. R is the radius. It's also the side length of all three sides. Therefore, the vertical side here is going to have to be 1/2 R. Or in the case of, since we're doing R equals 1, right? This vertical side is just going to be 1/2. Okay, and now we've got, we don't know what x is, so x squared plus y is 1/2 squared equals 1 squared. So x squared is equal to 1/2 is, 1/2 squared is 1/4. Subtract it from the other side. 1 minus 1/4 is 3/4, which means that absolute value of x is going to be √3/2. So where we end up having our y value be 1/2, our x value could either be positive or negative √3/2, which means that we could also do this one at the exact same time. Right, 5 pi over 6 is going to be blank, comma, 1/2. Oh, what is it? Yeah, right. Over to the right, it's positive x's, so this is √3/2, comma, 1/2. And over on the left, we have negative x's, so this is negative √3/2, comma, 1/2. In addition, we've also got the ones that are underneath. Well, this says that our x values are going to be just the same as the other ones that are vertically aligned with it. So this is going to be a positive √3/2, comma. This is now downward, so it's a negative 1/2. And over on the left-hand side at theta equals 7 pi over 6, we now have a negative √3/2, comma, negative 1/2. That's pretty cool. So now we've got all 4 of these things figured out. And this is one of those things, if your teacher's like, oh, you have to memorize the entire unit circle, guess what? No, you don't. You have to know what the values are for the first quadrant. I recommend proving them, like I'm doing here, and like work them out until you just know them by heart. Or, oh, hey, look, I can make a 30, 60, 90 triangle and shove it into any of these 4 spots, right? Where we have a pi on 6, irreducible pi's on 6, end up being all 30, 60, 90 triangles laid out the long way, right? Horizontally. And since I bring up the point, right? Hey, wait a minute. You just said horizontally. What about vertically? Yeah, you could do that too. How? Well, we've got all of these other ones, like 2 pi over 3, where we could look at this and say, hey, look, this is also a 60-degree angle here. The central angle is 60 degrees. And up top, this complementary angle is 30 degrees. So it's also a 30, 60, 90 triangle, which means that its side lengths are going to be the same as all of the irreducible pi's on 6. Now, the only real thing that you need to like worry about when you're talking about, oh, you know, I need to memorize all this stuff. The only thing you need to like memorize is knowing what's positive and what's negative. How do you do that? Don't create a mnemonic for it. Mnemonics are also potentially arbitrary. This is figure-outable. Right? You can work this out on the fly way before you ever have to take an exam on it or anything like that. Right? How do we do it? Which way is positive, which way is negative? Which way is positive, which way is negative? You already know. Right? Don't memorize which quadrant has what things that are positive or negative or whatever. Just look at the diagram. You know that your x's go this way, right? Positive on this side, negative on this side. You know your y's go this way. Positive on this side, negative on this side. Right, so our 2 pi on 3 ends up with a negative x direction, and it's the short side of the 30, 60, 90 triangle. Well, the short side is 1/2. So this is now a negative 1/2, comma. The tall side is going up, so that's a positive root 3 on 2. And then, again, think about the 4 quadrants. It's going to be the exact same thing. You have this one over here in the first quadrant, which is going to have a positive x because it's to the right. You're going to have a positive y because it's up. 1/2, comma, root 3 over 2. Going to the bottom, 4 pi over 3 has a negative x is negative 1/2, comma, negative root 3 on 2, because that's a negative y. Over on the right, theta is 5 pi over 3. Same deal. You now have a positive x, which is 1/2, and a negative y, which is negative root 3 over 2. Well, that worked out pretty nicely. Right? Now what's left? We have pi's on 4. Alright, how does pi on 4 work? Well, these are right triangles as well. They must be identical to each other in the x and y directions. Because now we have, again, a 45... That's a terrible 45, 45, 90 triangle. It's fine. Blarg. Nah, it's not gonna work. Alright, close enough. That one's better. Right? What is it in the x direction? It's x. What is it in the y direction? It's y, but it's also x. Right? Either one you want to do, it doesn't matter. They're all the same. And our radius is going to be 1. So what do we do? Well, it depends. It depends on which one you want to use, but it's all the same stuff. So who cares? It's x squared plus x squared is equal to 1. 2x squared equals 1. X squared is 1/2, which means that the absolute value of x is equal to, and in this case we get a 1 over square root of 2, or root 2 over 2. Depends on how you want to write it, but again, they're all the same. So, whatever, it's all good. So, 3 pi over 4 is going to have a negative x value, which is root 2 over 2, comma, positive y value, which is root 2 over 2. Okay. Down here, right, we have a negative x value and a negative y value. They're both root 2 over 2. At 7 pi over 4, we have a positive x value, which is root 2 over 2. We have a negative y value, which is negative root 2 over 2. First quadrant. X value, root 2 over 2. Y value, root 2 over 2. We just filled out the unit circle, right? And all it really took was a little tiny bit of mathematics using the Pythagorean theorem and knowing some facts about some special triangles. So we unfortunately cannot do the same thing with our Pison 12, the irreducible Pison 12. We're going to have to use a different method to get those, but that's all right. We'll talk about that some other time. All right, so what we get next is we want to come up with some sort of relationships that are going to exist on this unit circle that are going to talk about, for instance, we would like a function which is going to have an input of the theta value. We would like it to deal with all of our horizontal values. But here's the thing. It can't just be all the horizontal values, because the second we change the size of this circle, we're going to change all the horizontal values. But if we include the scale factor, like we were talking about before, where we scaled everything from whatever r was down to 1, or from whatever r is up to 1. It doesn't really matter which way you go, right? We're going to divide by the radius of whatever circle we've got, and that will shrink down to the unit circle or up to the unit circle, whatever. It will make it standardized for all circles. So take your x value, the horizontal value, and now we get to divide by the radius of whatever circle we've got. So take all your horizontal values and divide by the radius. Okay, now naturally we're going to want another one, g of theta, which is going to take all of the vertical values and do the same. Now we just figured that all this stuff out up top for when r is equal to 1. That means that f of theta is just going to be our horizontal values. And g of theta is just going to be all of our vertical values. Right? As a function of whatever angle we're at. So how does that work? Well, we can go like this. We're going to say that here's our theta, our independent variable, and here's our f of theta, our dependent variable. And then we're going to have to go through all these values that we just put on the unit circle. I would suggest 12, 16, right? These are 16 numbers. It's not terribly bad. Let's just stick with the pink ones for now, just to make it a little less cumbersome. So that's going to be 8 values. Technically 9, because we're going to go back around onto itself. We're going to start from 0 and go around to 2 pi. Okay, then we go like this, and we take all of those things and just shift that over there. And take that back, because that belongs to this pi. Right, so what do we get at each of these values? Well, these were all root 2 over 2's of some kind or another, or 1's and 0's. So at 0, right, when theta was 0, it was just straight over here. Where was our horizontal value? Well, that was 1, all the way out. At pi over 4, and in fact, we could just go all the way to the end again, because we know what that is. That's also going to be 1. To be fair. All right, our horizontal value, I actually encourage people to go out of order on this. Other side. That was a -1. Okay, and then top and bottom. Those horizontal values at pi over 2 and 3 pi over 2 are 0. And now we get pi over 4, got us root 2 over 2. 3 pi over 4 was negative root 2 over 2. So we're over here. 5 pi over 4 is that way. It's also negative root 2 over 2. And 7 pi over 4 is that way. That's going to be root 2 over 2. If you want, you can add in or replace all your pi's on 4 with pi's on 6 and pi's on 3. Right? Make it 2 of them instead of the 1 to give it a little more obvious curve as to what's going on. You could do that. Okay. How do we graph it? Oh, that was a terrible idea. Don't do that. Use the line tool. Okay, we're going to need equal values up and down. So we want to go with, a distance which is at least reasonable. We don't need to go to the right, to the left much. If we want to, we can also put a little bit more on the left side, just so that we could go backwards if we want to. Right, this is going to be 0. This is going to be 2 pi out here. That has a halfway point of, give or take, here. That has a halfway point of roughly here. And this one about here. And then halfways between each of those. That is about a negative pi over 2. And then we'll get a midpoint here and here. Much closer to the edge. Okay. Next, we're going to go up to a value of 1. And then similarly down to a value of -1. All right. When you're graphing these functions, I recommend start end. Right, 0, 1. Right, and this is theta versus horizontal values, which we could say like is your f for this, like the function f or the function values f. I would not recommend using x and y for this. You'll see why. Okay, it's going to end at 2 pi, which has this value of about 1 here. Pretty close. At pi, the halfway mark, it's at -1. At pi over 2 and 3 pi over 2, we're at 0. And at all of these pi's on 4, I like to call them quarter points. So you're going a quarter of the way through... no, it isn't. Nope. Well, you're going a quarter way through each of the upstrokes or downstrokes, but let's not go there. That's a terrible idea. Let's not do that. Then we end up going to root 2 over 2. How much is the square root of 2 over 2? Well, square root of 2 is about 1.414. So root 2 over 2 is about 0.707, which is under 3/4, but not by much. So I am known to mark out the 3/4 mark and then just put a point that's like under that a bit. And then it's going to also be here. And then we're going to have -3/4 about here, and then bump it just up a little bit. And there. Now we have 9 points, and this is going to look approximately horrendous at art. It's fine. You get better as you do it more often. Right. So this is the function f of theta, which deals with the horizontal values divided by the radius of the circle. Looks like this, and this will repeat. So at -pi over 2, right, negative angles are the same as their positive counterparts, just in a different location. So we go like this, we go from 0, we go down, or clockwise, pi over 2, that's down that way. So now at going straight down, we said our horizontal value was 0. And again, we have our point here for root 2 over 2. That goes there. Right, and then this one's going to do the same over here. Come down like that, and that's going to keep going off that way. Okay, these are periodic, meaning they will return to the same values. After one period. Oftentimes one period is denoted by the symbol tau. It's going to be just that certain distance, whatever it is. In this case, right, our tau for this is going to be from 0 to 2 pi. This is how long it takes for the whole thing to repeat itself over again. Not just from this point to this point, right? But also moving in the same direction. So how long is it going to be before all of the points within this period are going to duplicate themselves again and again and again in both directions? So in this case, that's 2 pi. From 0 out to 2 pi is a distance of 2 pi. We could have also measured this anywhere. So we could have said, let's try measuring from negative pi over 2, right? Where does that start repeating itself again? Well, it's going up through the x-axis. So up through the x-axis gets us 3 pi over 2. How do you find the distance between two objects? Well, we did that with the absolute value. You find their difference, right? Subtract them. 3 pi over 2 minus a negative pi over 2 is going to get us 4 pi over 2, or 2 pi. So it goes back and gets us the same value again, 2 pi, no matter where we measure it, right? When does this thing repeat itself? Okay, what about vertical values? That's depressing. There we go. So we go over here. There we go. Okay, now our vertical values are not quite exactly the same, so we will get rid of these anyway. Hey, why didn't you get rid of... No, really. For vertical values, what we've now got is all the y's as we go around. So we start with our 0 again. We start with 0 here because that's our y value for when theta is equal to 0. Right, off to the right, y is equal to 0. So our vertical value here is 0. 2 pi, we get a 0. Pi, the thing in the middle, right? So where were we here at pi? That was, again, a vertical value of 0. At pi over 2, that's a vertical value of 1. And at 3 pi over 2, that's a vertical value of negative 1. Then we're talking about all of our pi's on 4 values. So positive pi over 4 is up, so that's going to be positive root 2 over 2. 3 pi over 4 is also up, so that's positive root 2 over 2. 5 pi over 4 is down, so that's a negative. And 7 pi over 4 is down, so that's a negative. Right. So... Okay, so pretty much the same again. Here we have pi over 2 here, 3 pi over 2 there. 1 there. Right, so how does our vertical function look? Well, this is now g, not f. Right, g. Vertical values. Right, so we start at 0. Again, we're just to the right there. And then we end at 2 pi at 0, because, again, that's just to the right. At pi, that's just to the left, so that's also 0. At pi over 2, that is 1, and 3 pi over 2 is negative 1. And then at pi over 4, this is, again, positive root 2 over 2. 3 pi over 4, also positive. And then we move down to the negatives for 5 pi over 4 and 7 pi over 4. It's going to look like that. Similarly, if we then move down to negative pi over 2, our y value is negative 1. So that one's also going to be down here. And negative pi over 4 is going to have a negative root 2 over 2 vertical value. So that's going to be there. Right, and then that's going to keep going in both of those directions. Again, same deal. The period here is going to be 2 pi. It's still periodic. Right, we can show that's going to go from here 0, 0 to 2 pi 0. And again, doesn't repeat anywhere in between there. Doesn't repeat the same behavior in the same direction, all that good stuff. Alrighty. Yeah, we'll go 1 more hour, I think. So I'll see you all in 3 minutes. We're going to start an ad break. And if you have any questions that you would like answered, go ahead and pop those into chat or over to Penn Center's Discord. If you're not part of the community, we'll figure it out. Just pop it inside the chat and we'll talk. All right, see you in 3. Thanks for being here. Good evening and welcome, everybody. Now. Arts and crafts keep exploding all over this room. Alright, so we learned the last two moves in our Tai Chi form, so I figured this would be a good expenditure of our time. Got to practice a little bit. So,
Rating party!
it's a rating party. Academy of Useless Ideas. Good evening and welcome, everybody. Thanks for coming on over. We were just talking about trig, and I I redeemed myself doing a martial arts form. So I thought tonight we'd do the Tai Chi form that I have learned for the last 6 weeks or so, and we finally got. I'm now working with another lady, and the two of us finally learned like the next two moves. So we start from a neutral forward stance. From here, let the arms go forward, and they come up, and kind of push, and then go down while exhaling. Create a small ball of energy as we lean over and start twisting into our hip, which adds a bit of power and allows us to step out with this one. We come across and then and then we do our ward off from here. So our hands come around and then back into this position. Our rear should work on the heel. So yeah, you should go from here to here using the heel of your foot, which is like really weird for me being a karate person. Normally when you're here, you want to drop into your power, so use the front of your foot to then be able to drive something. But here we want to actually maintain our like posture. Very weird. So here we actually use the heel of the foot to maintain posture. Right, so then from here, you're gonna tuck your butt under as well. If your coccyx ever feels like it's kind of like going out, you have to like make sure that you're actively tucking it under with your muscles. It's a little weird. So we go from this ward off position, we come just across a little bit, and then bring this back while we sink, while leaving our right hand out where it was. Come across, and then here we tuck our hands in and bring them back and do a that was it. Now it's this way. Do a gentle like shove, and then we break our hands apart and then lean back on the back leg, while at the same time tuck under while at the same time not allowing our coccyx to go any further than, I think it's halfway down your calf. And when you do this, it adds a tremendous amount of power. So like if I'm here and I just like allow myself to move forward, so I just like pick up my front leg, there's a lot of tension between my feet. And if I pick up my front leg, I just naturally kind of fall forward. You use that in order to take all of the momentum from your body and just allow it to push the other person. Like you're not shoving with your hands, you just are using your entire body and using all of that weight, especially if you come down a little bit. You're using a small gravity assist as well, and you can do a tremendous amount of shoving with just using your body and your body weight, gravity, and momentum. So it's amazing to just see all this in action, because like, you know, my instructor will actively try to just hold a position like this, and then I will just have to, you know, use physics essentially to break his posture and then move him. And he's bigger than I am by significant margin. Anyway, come across like that, we go like that, down, across, we go into a push, and then back onto the back leg. Here's the new part. So we are doing what's called a pluck. So essentially you're grabbing somebody's wrist and then pulling them down, pulling their arm across you as you're going like this, and you're bringing your front leg from this position back to about here, and then we move our left leg again forward, and at the same time we are actually doing a strike, which is one of the first times we've actually done a strike in Tai Chi. But essentially we're letting our entire momentum dictate how much energy is going into our arm. So it's essentially a motion that's going to ripple up from your anchor leg into your midsection into your arm. So we go from here, we're doing this, come back, right, we do a pluck, bring it down, and then come around and hit here. And it's either usually a rage hand like this, or he's done it just as an open palm. And it's using a lot of the same stop mechanism with your left hand that Eskrima does when we were doing our outside strikes. So this is causing the front hand to whip, and then that causes the stick, or machete if you're using a machete, to go further than where you're actually stopping. It adds an extra like 5 or 10 degrees onto the whip. And it also puts the energy that's in your entire arm up into the front of your arm. So it gets to be pretty serious business. And then once all the way through. That's the wrong one, isn't it? Yep, I'm supposed to do ward off. Try again. Righto. So for the rest of the night, we've been working on trigonometry and trying to define it. Salient points and things that people find interesting. We have I try to define it. Come on, there we go. I try to define it a little bit different for like everybody else, because I know not everybody's interested, but essentially we've got our 360 degrees comes from the Babylonian number system. It's kind of arbitrary in that it's like evenly divisible by a lot of numbers, but that's about it. So instead, we could use this system where we start talking about what is the total circumference of a circle. It's 2 pi times r. And if we let the entire circumference of the circle be our angle, i.e. that r is equal to 1, now we can just say that the arc length around the outside of this unit circle is the angle. So our theta, this arc that we put on the inside here, is just the same as whatever our arc length was around the outside of the circle. Start from 0, and then we're incrementing by pi's on 12, going all the way around. Hey Ads, how's it going? So as we go around, it's incremented by pi over 12. We're only going to be using the ones that are going to give us nice triangles. So in this case, our 45, 45, 90, 30, 60, 90, and the 4 cardinal directions. Those are nice triangles in that they aren't triangles. We were able to calculate how to get root 3 over 2 and root 2 over 2 as these numbers for x's and y's to get positions. If anybody missed all that, it's going to be on the VOD, so feel free to go back. But my point here was that we were going to, in order to get all these angles, just increment. So we split the whole thing in half. You've got 0, 2 pi if you go all the way around, pi if you only go halfway. If you only go quarter way, there's pi over 2. Sorry, pi over 2. And then that's 1 pi over 2. That's 2 pi over 2. That's 3 pi over 2. And that's 4 pi over 2. No, that doesn't quite work, but that's 4 pi over 2. So we're going to increment every time that we go around from 0 to 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And then we split those in half, and we go pi over 4. Okay, that's 1 pi over 4, 2 pi's on 4, 3 pi's on 4, 4 pi's on 4, 5 pi's on 4, 6 pi's on 4, 7 pi's on 4, 8 pi's on 4. And then we said if we want to have like equilateral triangles, we can go with pi's on 3, which are going to get us nice equilateral triangles either here or pi on 6, where we get nice equilateral triangles going sideways. And that'll allow us to get these positions. So equilateral triangle here means that we have R, R, and R. So each of these is R over 2. And then we use Pythagorean theorem to get the third side there. Isosceles right. We said that the legs have to be the same size, so x squared plus x squared is 1. Figured out that those are root 2 over 2. Okay, and then we said based on all of these locations that we get for all of these values, all of these angles, we then want to create some functions. So f is going to be this horizontal value function, but the problem is that if you scale your circle up or scale your circle down, you're now going to get different values. So instead, we do the horizontal value divided by the radius, which now gets us the same f value for each individual theta, no matter how big or how small the circle gets. So 1 theta gets us 1 value. That's what we're going to care about here. Okay, so we already know what these functions are. I tricked you. Ha ha ha. right? We're just learning it a different way. So this f function, right, starts at 1 right here, and as we increase our angle, it decreases, goes down to -1, comes back up to +1 at the end of the period. It's periodic. It has a period of 2 pi, right? We know what function this is. Those of you who have been here a while, right? I mean, hell, I even tricked you with the horizontal value thing. Guess what? The horizontal value compared to the angle you're looking at is the adjacent side. The radius is the hypotenuse. So what is the adjacent over the hypotenuse? Right? So f of theta is equal to the cosine of theta. That is the cosine function, the same one that you probably already know. Right? G, we're looking at vertical values. Well, vertical values that start at 0, go all the way up to 1, come back down to 0, back down to -1, and then back up to 0. Again, vertical. The vertical side here is opposite the angle here. So opposite over hypotenuse.
Find all of the songs of the summer in one playlist. Summer Hits 2025. Featuring hits from Rose and Bruno Mars. Clean Bandit. Fred Again.
Which means that g of theta is just the sine function. Right, same sine function that you're probably used to using in other contexts as well, when you were doing right triangle trigonometry. Oh, look at that. This was right triangle trigonometry all along. We're just using the unit circle as well, right? Bring the two things together. Okay. So that's it, right? We're done? Okay. So there are other things that we can do. We need another unit circle. Maybe we could use that one. That'll be fine. I don't really want to use a lot of the other ones because they're getting, you know, a little crowded in there. So if we go over here, throw this down, and let's get rid of, let's just get rid of these other colors again. We'll use blue. Damn. That's going to be a pain. Actually, it's not. We just need to do it a different way. Okay. So, next thing we do is to say, if we want to look at this whole picture, we've got kind of two different ways to look at the next trigonometric function that we want to look at. Right, one is that we build a line which is tangent to the circle at 1, 0. Okay, this is easy enough. It's not like it's... it's not like it's particularly difficult to use or whatever. This creates another right triangle, which is, again, a scaled up version of the original triangle. So instead of having x, y, and r, now we have, if you notice here, this is just r again. And then we have this other side here, the hypotenuse. And we have this side here, which goes from, again, the bottom of this corner where we are, wink, wink, nudge, nudge, right? What kind of line is this compared to the circle? Well, it's going to hit the circle at exactly 1 point, 1, 0. This is the length of the line which is tangent to the circle at 1, 0. All right, this one over here, this is going through the circle. So this is going to be the length of the secant. All right, how can we relate these things to the other stuff we've already got? Right, we've already got a smaller triangle, and so we can do proportionality statements to get these other lengths. So the ones that we have are going to be, for instance, if we go x compared to r, we're taking x, the short length, and going just out to the edge. So short to long. We're not going to do x to r this way, right? Or this way. We're not going to do x to r being its own radius. We're going x to the other triangle's x, which is r. This is not confusing, I promise. Is going to be equal to, right? Now do the vertical one. So the vertical one is, well, this was x here, so this one needs to be y, the shorter one, compared to the longer one. Okay, so what we have here now is if we were to rearrange this, we're going to have the tangent over r is equal to y over x. Now, if you remember from earlier, we were saying that this is going to be the scaled down version. So the tangent on the unit function is going to be, or on the unit circle, is going to be y over x. Well, that's pretty cool. Right, so the tangent on the unit function, no, the tangent on the unit circle, there we go, is going to be y over x. Well, that is, if you look at it, compared to the angle theta, that is the opposite over the adjacent. Hey, wait a minute. That sounds familiar, doesn't it? Right, the tangent that we're always talking about always has to be the tangent of theta referring to what it would be on the scaled down unit circle. So like this is a unit tangent function, essentially. You could, in theory, scale it back up to whatever size circle you wanted, but like that's just going to be, it's going to get messy. I mean, not really, but... Okay, what about the secant? Well, we could do this secant length by doing the same thing. So we compare x to r, and then we compare, notice that this is now the short hypotenuse is r, compared to the long hypotenuse, which is that secant. Yeah, thanks for coming in, David Van Housen. Hope you have a good evening. I'll be back on Friday for game type stuff. We're probably doing Against the Storm again, and I might be back in the meantime or sometime this weekend, depending on what our schedule is looking like. It's looking like it's going to be pretty crazy, but you know, that's life. But thank you for coming in. Right, so we have this secant over r is going to be equal to r over x. So this secant on r, again, is like the secant unit function, which is r over x, which is then going to be the same as the secant of theta being equal to r over x. Right, that's our unit function, unit secant function. It's r over x. We saw that, didn't we? Not quite. So here are adjacent over the hypotenuse, the horizontal values over the radius. This was x over r. And now we just found the secant, which is r over x. So that means that secant of theta is going to be equal to 1 over the cosine of theta. That also means that on the unit secant function and on the unit tangent length, unit tangent function, and on the unit radius, we now have another Pythagorean triangle that we can use. Right? This says that 1 squared plus tangent of theta squared. It's better if we do it the other way. Tangent squared of theta is equal to secant squared of theta. Right? That just showed that we have now that entire Pythagorean relationship. Interestingly, right, if we look at the secant, well, that was 1 over cosine squared theta. This was a 1 over here plus the tangent squared of theta. What's tangent squared? We had y over x. On the unit circle, r is equal to 1. So that means that f of theta is really just going to be equal to all of our x values, all of our horizontal values. That's it. It doesn't have to be scaled because of the radius. The radius is 1. Right? Only on the unit circle. Only on the unit circle does this work. And the same can be said for the sine function. The sine function was y, the vertical values divided by r, y over r. Right? So this really is also y over r over x over r. So really that's the sine of theta divided by the cosine of theta. So this is 1 plus sine squared of theta over cosine squared of theta equals 1 over cosine squared of theta. Now I don't know about you, but I don't really like having these fractions here. So if we multiply through by cosine squared of theta, we end up with a cosine squared of theta plus a sine squared of theta is equal to 1. Well, how do you like that?
Bring the beats with premium. Download and bring your music anywhere, so you can dance to high quality music without hearing ads.
Okay, now if I'm right, okay, you can also, I should have saved it, or should have copied it when it was cleaned up. Didn't think I'd be using it again. Isn't that just the way? So anyway, if we clean this up a bit, and then we draw a horizontal tangent to our unit circle. Okay, pretty close. This stuff, it's a tangent, so it meets the circle at a right angle at the end of its radius. Then it also crosses up here. Hey, Pen, how's it going? Now this angle here is not theta. Almost always, right? This angle is the complement of theta. So this is pi over 2 minus theta, which is its complement. But then the angle over there, right here, is going to be the complement of theta, which is itself theta. Okay, alternatively, this line here and this line here are parallel. This is a transversal. Theta here and our mystery angle up here have to be opposite interior angles, so they are equal to each other for just the reasons that I stated in terms of complements. Okay, so we know that that angle up top has to be theta. Now, if we do trig on the triangle that we've just created, we've got, yet again, r here. This is the tangent length of the complementary angle to theta, or of theta. And this here is going to be the secant of the complementary angle to theta. What do you think we should call them? Right? If this is the tangent, of the complementary angle to theta, then I don't know about you, but I think we should call it the cotangent of theta, the original angle that we were talking about in the first place. Right? It's called the complementary tangent, cotangent. Just like if we want to argue about it, we could go all the way back up here. I don't know which one I want to do here, but it's fine. You could use a complement, yeah. I like your hat. Right? We could do a complement to this particular point using this particular angle, right? Pi over 2 minus theta. Still the same angle, but now we've got here our y distance here and our x distance here. So if we only want to think about like the sine of the complement, this is x over r. The sine of that particular green angle, right? The sine of that is going to be opposite over hypotenuse, x over r, which is equal to the cosine of theta, right? Complementary sine. Complementary tan. All right, that's fair. Not exactly what I said. So now we've got all of the names, at least, of all of the functions and their complementary functions. This also means in this one, we now have another right triangle trigonometry, or we now have another Pythagorean Pythagorean relationship that we can use. So this is 1 squared, because again, r is 1 on a unit circle, plus complementary tangent squared of theta is going to equal the complementary secant squared of that angle. I gotta tell you, every time I try to come up with one of these Pythagorean theorems, or at least those last two, with the tangent and the cotangent, for some reason I can never remember the order in which they actually went. Right? I was always like, is it 1 plus or 1 minus? I don't remember. Like, where does it go in all this stuff? It was nonsense. I mean, it wasn't nonsense. It was just, it was seemingly arbitrary to my brain, because where did these all come from? This is what I was saying earlier. Once you know how something comes about, then all you have to do is reactivate that one little part. and just be like, okay, look, this came from our x, y, r triangle, right? Sine squared plus cosine squared equals 1. That's it. Once you know this one, then all you're going to have to do is divide by cosine squared in order to go this way and get that one. Divide by sine squared and get that one. Right? So this is going to be cosine squared theta over sine squared theta plus, well, that's 1, so equals 1 over sine squared theta. So now this is going to be, again, this is cotangent squared theta plus 1 is equal to cosecant squared theta. Ew. Close enough. Hey, does that? Yeah. So as long as you know the basic one, the other two now just become derivations. But also, if we know how to get them, right? Get the scaled up triangle. So now instead of just using XYR, now we can use this one. It's the tangent, the secant, and the radius. And we can go the other way and get the radius, the cotangent, and the cosecant, which now use the complementary angle. All this stuff becomes so much easier when you start learning the geometry that exists behind it. And it took me until I taught it like 30 times before I really got it. Before I was like, hey, wait a second. All right, and then the other part. There was one other. Ugh. This is fine. How many times will I say that, oh yeah, I should have done this when? I mean, that's kind of silly, because I need that. Brain not braining. Come on. What was I doing? What was the one last thing? Oh, right. Do it the other way. If we do this the other way... Ugh. There. Copy that one. Much better. Okay, so now no, I do actually want to take that and move it down. Alright, watch this. Instead of doing those two, we could also do this one. Draw the one tangent that exists at that point. At the point xy. Why? Well, it creates right angles here and here. It creates a secant here. It creates a... Well, okay. Sorry. This creates a cosecant there. Have to be careful. It creates a cotangent here. It creates a tangent length here. It creates a secant here. Right? And I will grant you, right, these are the 4 trigonometric functions based on r being equal to 1. So it only really works if r is 1. Otherwise, they've all been scaled up by a factor of r, or scaled down by a factor of r, and you need to fix that before you actually figure it out. Right? This at the bottom here is going to be then a cosine of theta, and this right here is going to be the sine of theta. Again, provided that r is 1. All 6 trig functions in one picture.